In this video, we're going to get into some of the control logic design decisions that we need to make. It's going to be another installment of The World According to Adam. Now, I hope you realize that I'm expressing my opinions and I'm by no means an expert. And while I would never give you bad or incorrect information on purpose, I may not be portraying what is the best practice or the best option. And I'm learning as I go through this, so some of these decisions may need to be revisited. And The World According to Adam implies that this is going to be far more of a discussion video than it is going to be a build video. As a matter of fact, I have nothing planned to build. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. So I learned a long time ago that the first thing that needs to happen when you're facing a complicated problem is you need to put some definition to it. And this is no exception. There's a lot of things that need to be orchestrated, and the control logic is like the conductor of an orchestra. It has to orchestrate how the entire system is going to interoperate properly together to get deterministic, measurable results. So the registers in particular have more than 10 different operations that can happen on each register, and I'm looking at something like 32 registers at the moment. So you can do the math there. It gets to be pretty significant, the number of things I'm trying to orchestrate here just in registers communicating with registers, or registers communicating with all other parts of the system. Each operation has its own timing requirements. Some things are rising edge, some things are active low, some things we want to have happen on a falling edge, so we need to address that in some way, shape, or form. Some signals may need some delays or some augmentation to maintain deterministic behavior, meaning that I can't latch a register before I increment the counter, as an example. That is not giving us the correct result. And if I latch it at the exact same time, I have a race condition that needs to be managed. I need to be able to support all the different instruction requirements, and there's several different instructions that may or may not be able to be handled depending on what we define and how we define it. So we want to think about those things ahead of time and allow the control logic to do whatever it needs to do in order to support the instructions that we're going to need. I have a couple of examples that we'll talk about in a little bit. We also need to define and standardize how we want the control module signals to operate, and we'll get into that. We've got some decisions around how we want to handle that as well. I'm not talking about standardizing to make everything operate the same, but our approach to how we want to design those signals so that the control module can handle that. Several operations are actually mutually exclusive and can hurt the hardware if they happen at the same time, and so we need to protect those. We need to take a moment to make sure that we don't allow hardware to do something that's going to hurt itself. We need to look at what signals get extended to the register, or more generally each module. Specifically the clock. Does the clock actually need to be extended all the way to every module? And several signals may be required to execute any given instruction. For example, in our register, we've got an increment function that we've defined, and we've got a latch function that we've got defined. And increment for a program counter is going to need both of those signals, so we need to extend both of those. I do want to take a look at a guiding principle, and that is to make the control logic conform to the actual register, or more generally the module requirements, rather than modifying the register or module to conform to a common control logic interface. So what I'm calling register input operations are things that will change the contents of the register. So we've got a clear reset, and of course we need to latch that, meaning that we need to encourage the counter to be cleared, but we also need to clear the actual register, and that has to happen through a latch operation. This needs to be asynchronous, and it needs to be tied to the power supervisor. I'm not anticipating any direct control logic for this. There's not going to be a clear instruction per se, without actually renaming something that already exists, like XOR a register to itself. Increment the counter and latch. I've talked about that as part of the program counter. Again, different signal requirements for each of those. The count actually happens on a rising edge on a clock cycle, but the latch actually happens also at the rising edge, so there needs to be some kind of a delay in there that is handled. Decrement is similar to increment, but it's mutually exclusive with increment. I cannot pass both signals to the counter at the same time. The hardware is non-deterministic on that, meaning I don't get defined results. And then load from the main bus and latch the register. Again, we need to load the counter and the register, different signal requirements, and that also makes no logical sense. While it can happen, but it makes no logical sense to do that with an increment and decrement. So is that mutually exclusive? Technically, no. Not from a hardware compatibility perspective or a hardware protection perspective, but it's not something that we want to allow because it makes no real sense. And finally, there's an input operation called do nothing. And we need to take that into account and understand that that's something that we need to plan for and have some method of sending or not sending signals to a register or a module when nothing is to be done. We need to be able to handle that in the control logic in some way, shape, or form. Similarly, we have several data bus operations, and data bus timings are going to be separate from the address bus timings. We'll look at that in a minute. But we can assert a register to the ALU A side. We can assert a register to the ALU B side. And we can assert a register to both sides of the ALU. If I wanted to add a register to itself, that's a very valid operation to do in any computer, and therefore something that we want to be able to support. So we've got to be able to assert a register onto more than one things at the same time, specifically ALU A and ALU B. Potentially we could assert also to the main bus. And we can assert to the main bus in byte swapped order. Now we don't want to do those last two concurrently because they are mutually exclusive, but we do want to make sure that we are allowing something to go to the main bus or the main bus in byte swapped order. And then again, there's a do nothing with the data bus. Address bus operations, we've got assert to address bus 1, we've got assert to address bus 2, and again, this is for any given register. So while one register is asserting to address bus 1 and a different register is asserting to address bus 2, the address bus operations for all of the registers would be do nothing, and so we have to account for that as well. But it's not quite as simple as that. Consider a couple of examples. If I wanted to take the contents of R1, R1 being an address, so I want to load the contents of memory pointed to by the address that's stored in R1 and load the value that's in that address into R1. This is something that a compiler would do quite frequently. I need to be able to access both the address bus as well as the data bus, and register R1 needs to be able to do that simultaneously. Again, second example, if I want to take the value that is in R5 and store it to the address that is pointed to at R5. This might be, for example, a pointer to self. Again, I have the need to be able to access R5 through both the address bus and the data bus at the same time. Plus, we need to make sure that there's time for the memory address to stabilize before reading or writing. So the timing of all of that has to be clear as well. So clock cycle timing, and I went through this in video 9. Clock cycle timing, the address bus is going to be asserting the address onto that bus for memory for the entire cycle. In the previous instruction examples, the memory address is going to be asserted onto that line for the entire clock cycle. and we're going to assert a new value or new address onto that address bus at the high level. The data bus assert, on the other hand, I want to take care of only at the low level operation in preparation for that rising edge, where at the rising edge we actually input or latch or store the result of that operation. And of course, I may need to revisit some of this timing as well. So to put this in more of a graph form, starting at the high level, I'm going to reassert the address onto the address bus. That address is going to be asserted through the entire clock cycle, and then on the high level, right after the rising edge, it's going to have a new address that needs to be reasserted. And then on the high level, we'll deassert on the address bus. On the falling edge, we'll take care of the counter increment, counter decrement. Those are rising edge operations. So for us to conform to that, we'll have to flip or invert that signal from the clock. Then at the low level, we're going to do the data bus assert and our counter load. If we're loading anything from the bus into the register. And then on the rising edge, we'll latch those new values from the counter into the register. And so if you look at the previous clock cycle definition, I started with the rising edge as the first element in a clock cycle. And some things have moved around a little bit. I've removed the stabilization portions of this. I've added a couple of things specific to registers. But the big key here is that the rising edge is really the end result or the culmination of all the work that we've done in the clock cycle leading up to that. So it doesn't make sense to start the clock cycle conceptually with the rising edge. It makes a ton more sense to end the clock cycle with the rising edge. And so I've had to change my thinking on this, and you'll see some differences in how I represent the clock cycle definition and the fact that I'm actually starting the table with the high level and ending with the rising edge, whereas before I started with the rising edge. So I'm changing my thinking on this. So if we go back and reconsider that load from memory in register R1 into R1, taking that new clock cycle into account and when we want to do things, on the high level, we're going to assert R1 to address bus 2. On the low level, we're going to assert the memory that we asserted onto address bus 2 onto the data bus. And then on the rising edge, we're going to latch that data into R1. R1 does not change until the rising edge, at which point we're going to deassert the data and at the high level and reassert a new address if there is one in the next instruction. Similarly, if I'm going to take the contents of the value in the register R5 and store it into the memory at location R5, I start at the high level. I'm going to assert R5 onto address bus 2. Falling edge has no direct activity associated with it. The low level, we're going to assert R5 onto the data bus and assert write enable for the memory. And then on the rising edge, we're actually going to store that final value on the data bus into memory. So generally some control logic decisions that we need to make. Do we want to extend the clock to the register and in modules in general? For example, do we latch on the clock, or do we have a dedicated latch signal associated with that? And for now, we're going to say no, I don't want to extend the clock to each module. We're going to have a dedicated and latch signal that goes from the control logic to the individual modules, specifically the registers. Some things that are mutually exclusive need to be multiplexed in order to maintain that exclusivity. And so do we demultiplex those signals at control or at the register? And my opinion on that is, where is the requirement for exclusivity? So for the address bus and the data bus, where you cannot assert multiple things onto the bus at the same time, one of the keys is you have to control that at a global level. One register is not able to lock out all the other registers from asserting onto that bus. So the control logic will have to be responsible for demultiplexing that and passing that information onto the register. And the register then needs to assume that all of the blocks are in place, that it actually, when it has control, it can perform that assert. On the input, on the other hand, the register itself should maintain that control to assure exclusivity. That means that we would be passing on a multiplexed signal to the register, and the register would then need to be able to provide some protection to say, hey, I'm not going to do this. I'm not going to do more than one thing at a time, because it could end up hurting the hardware or giving indeterministic results. Do I want to adjust signals at the controller, at the register, or at the module, and more globally, such as signal inversion? If there is something that we want to have happen at a low signal or on a falling edge, but the register itself requires that it be a rising edge operation, do we want to invert that signal at the controller, at the register, and more generally adjust signals at controller, at register? And my opinion on this is that I want to keep the register as native as possible, or each module as native as possible. Meaning, if I have to make a decision to adjust something, I don't want to do it at the register. I'd rather do it at control. And the reason is that if I find out that I'm doing something incorrectly, I don't want to have to create a new signal at the control that undoes a decision I made in the register. And I would approach that farther down the road if I ran into something like that. So from that perspective, I want to make sure that the signal that leaves the control and goes to the register is in the native register format. And then LED displays of the signals, do I want to do that at the controller, at the register? And my feeling is I want to put those LEDs at the register. And I want to do that so that I can actually determine what's going on close to where it's actually happening. I mentioned this before, I'll mention it again. Register change functions or inputs are all generally mutually exclusive to the same register, but not necessarily across all registers. So we do want to decode that at the register. The clear and reset, the load, the increment, decrement, we want to be able to decode those at the register and have those signals bundled together to reduce the number of control lines that we're passing on. But bus outputs must be mutually exclusive. If I assert multiple things onto the same bus at the same time, it's going to harm hardware, and we can't allow that. So we want to be able to control that at the hardware level, and that means that I have to run additional lines, more than I would if it was multiplexed going into the module. I have to run additional lines for each control to each module. So our register control signal decisions. The clock will not be extended to the register, at least not at this point, and more generally any module. A control signal will be used to handle everything, and that control signal will be formatted such that it can take the place of a clock signal if need be. Increment and decrement will be demultiplexed at the register itself, and it's a self-preservation decision. Output bus asserts will be demultiplexed at the control logic. And again, that's because it has a more global view of everything that's going on. A multiplexed value of 0 will be used to do nothing, meaning if I have 3 different controls that are multiplexed together, and I have the values of 0, 1, 2, and 3 that are possible on 2 bits, 0 will be used to do nothing, 1 will be used to do option A, 2 will be used to do option B, and 3 will be used to do option C. Any signal that includes and latch, and specifically in the registers, but may have other modules that have that, those operations will be in a separate control signal leaving the control module. It is not going to be handled and decoded in the register itself. This means that I have the ability to handle this in firmware, as opposed to having it hard-coded and decoded in the hardware logic, which A, gives me more flexibility, and B, reduces the number of gates I have to pass through to get the signal to the actual control, and therefore should be faster. All signals will be extended to the register in their native state. In other words, no in-module inversion. That's all going to happen in the control module. Signal delays will be handled at the control module. So if I need to ensure the AND latch happens after the increment or decrement, that signal will be handled in the control module, not in the register itself. More generally, anything not explicitly required at the register or more generally in any module will be handled at the control. So that control logic will handle more general requirements, and the register, if it's required to maintain its integrity, will be handled on the onboard on module at the register. And finally, I'm not overly concerned with the size of the control word. That could be 80 bits wide to control everything that I'm going to control. I am not concerned with that. While it does add significantly to the hardware, I'm more concerned in my project with speed over keeping my chip count down. For the register, I need to complete the main bus wiring, and that includes connecting the output onto the main bus up to the inputs in front of the counters. I need to still troubleshoot the single step bounces that we saw and I glossed over quickly in the last video. And I'll put something up in the upper right hand corner so that you can see that. I believe it was a race condition and therefore was handled properly by adding the inverter. And so far I said I was going to take the inverter off that register. I have not done that yet so that I can actually confirm that A, it was a race condition, and B, that the inversion actually solved that problem. I need to complete the control circuitry on the register. And then finally, I need to move my entire design into KiCad so that I can order some printed circuit boards. And again, if you'd like to see that, let me know. For the control module, I'm going to depart from how others have done this, and I'm going to take the definition of the assembly opcodes, instructions, and the operations to complete those early in the project versus adding them in as I go. And so I'm going to move this up into the list relatively quickly so that we start looking at some of the operations that we want to be able to do and defining what an instruction looks like. Taking care of defining the opcodes early in the process is going to make it easier for me to explain what the hardware is doing, because I will have some components to match that up to demonstrate some of my decisions. And finally, I still have my parked items for the clock. Those are going to be inserted in as I have time. Thanks for taking time with this video. We'll see you again soon.